How are things going?
Good. I
Y-
ordered that book you recommended,
Yeah.
Oh, the
but
mystery novel.
yeah, because I read the description. It seemed good. So, but I have to wait for it to come.
Yeah. Actually, in the second book, that case is is referred to as bear bait.
Oh, why?
Yeah, but you read it. It's interesting. There's interesting characters in it.
Okay.
I actually have an extra copy of one of the books. If one of them, one of you want to have it.
Oh, so
I'll take
we
it.
go to your place and pick it up?
No, I probably would send it to you,
Ah,
or I would put it in your mailbox. If you have one at CSUN.
oh.
I'll take it.
Angela has a mailbox in the system.
Yeah, I'll put it in your mailbox. It's the fourth in a series, so there's a whole lot of reference to earlier ones, but it actually makes sense without the earlier ones.
Mm.
Yeah, next time I get to see some, I don't know when that is, I'll leave it in your mailbox.
Mm.
Okay. So let's see what we're gonna. Did anyone find a misprint in the reading?
I didn't find one. Was there one?
Right. Well, you didn't find one. So did anyone else find one?
Not yet.
No.
Well, there is one.
Okay.
So we all have about Dini numbers. First of all, everyone agrees that the sets in which Dini numbers are greater than something or less than something, that they are measurable.
Yes.
I mean, so if you go to page 123, on the very bottom, where it says, therefore, m of e sub gamma goes to 0 as gamma turns to infinity. And since the set d upper plus of f less than infinity is contained in E gamma for any gamma. That implies the upper plus of f of x is less than infinity almost everywhere. The misprint is here. This should be an equal sign.
Mm.
You agree?
Okay.
Because otherwise the conclusion would be that the measure of the set
Mm.
is 0, so meaning that the upper plus of f is infinity almost everywhere. So there's a misprint in the last line. Are there any other questions about the reading? I know it's pretty, let's say it, it's not easy reading that proof with linear numbers. So are there questions? Which could be clarified or not?
Professor, again, please explain why is equal again.
Well, I mean, they draw the conclusion that the conclusion they draw is that d upper plus of f of x is less than infinity almost everywhere, right?
Yes.
In the bottom.
Yes.
If this set, if this thing would be correct, if this would be correct, then the conclusion would be this.
Oh, yeah. Okay.
Right?
Yes, you are right.
And that's the opposite of this one.
Oh.
Yeah.
Okay. Okay. Yes.
Right? It should be equal or greater than or equal to, but it should be not less than or equal to. Because what we want to show is that, well, the set where it's not less than infinity, that this set has measure 0.
Can you go through the proof of 3.6, just the basic ideas in it?
Not 3.6, 3.4 you mean.
Oh,
3.6 is the correlate. Well, the basic idea is you have these 3 approximations to a derivative, 4. The upper plus, the lower plus, the upper minus, and the lower minus. And you want to, the idea is you want to show that all 4 of them are equal almost everywhere, right? So the first part is, well, the upper plus, which is the lim sup, is always, I don't want a keyboard, it's always bigger. I'm struggling with technology here. It's always bigger than the lower plus, bigger or equal to. So if we can show that the set, the measure of the set, where it's not big equal. Where this well, the complement of this, that this measure is 0, then all 4 of those Dini numbers are equal almost everywhere. So then the second step is to show that the set where D upper plus is infinite has measure 0. Right? And this is the proceedings in the lower half after we recall of page 123. And now when it gets complicated, they introduce on 124, they introduce that set, the set of all x in the interval AB. And remember, f, we assume, is an increasing function such that the upper plus of f is greater than r, and the lower minus of f is less than lowercase r, where capital R is bigger than lowercase r. And the idea is show that the measure of E is 0. And if the measure of that set E is 0 for any kind of R, you let capital R and lowercase r run through Q. And that means they can get arbitrarily close to each other. And this will show that the set, I need a little more space here. Okay, I'm going to go to next whiteboard. This will show that of all x such that D plus is less than or equal to D minus, lowercase minus, is equal to the length of the interval. And that means this happens almost everywhere.
You mean the measure of the set is B minus A?
Yes. Of course.
Okay.
Of course. So in the first step, they say that if they look at the set E, which I had before, then there exists an open set O such that O contains E, and the measure of O is less than the measure of E times capital R over lowercase r. So remember, capital R is strictly larger than lowercase r. So this fraction is strictly larger than 1, right? And what we have is, since E is a measurable set, and E is a measurable set by definition of it, we have essentially, since E is a measurable set, there is an open set which contains E And the measure of the open set is the measure of E plus epsilon, and the plus epsilon can be approximated by a capital by a ratio of two rational numbers where the numerator is bigger than the denominator, right? So since O is open, O can be written as a union of countably many open intervals, right? We had that any
Yes.
open set in the real spheres in R, not in higher dimensions, one-dimensional case, which are disjoint. The union of countably many disjoint intervals.
This is theorem 1.3 and chapter 1.
Yes. There's that's
Page 6.
right. So then you use corollary 3.6. And corollary 3.6 says it's essentially a corollary to the sunset lemma. That the set of all x in AB, so the set of all x in the open interval AB, such that g of x plus h is strictly larger than g of x for some h, so not for all h, just for some h, that this is a disjoint union of open intervals AK, BK, where G of BK is equal to G of AK. Okay, so if you look at this original set here, where D plus is greater than D minus, that tells you that f of x plus h has to be strictly greater than f of x there. Applied to this function, g of x. And then what they do again, so for each of these open intervals an, bn, if you apply this to this function negative f of negative x plus lowercase r of x, you find that this is a union of AKB intervals, so each IN where f of bk minus f of ak is less than or equal lowercase r times bk minus ak. And then you use this lemma again for the third time now. So here's the third use of the lemma. Which says each AKBK is the union over J of sets AKJ, BKJ, and you apply it to this new function, f of x minus capital Rx, for which f at bkj minus akj is now greater than or equal to capital R times bkj minus akj. So now we have this, yeah.
So this g function is a different g mentioned in the paragraph above.
Exactly. You use a different g.
Okay.
But you use the same lemma. And then you put everything together. You get the measure of your open set O. I think that's a misprint again, but
there's no subscript n.
There shouldn't be a subscript then, yeah.
But they get that O sub n is with a subscript k and j.
You get that this is equal to, since now you have still a countable union of open intervals, right? The measures of these guys, which is just minus akj, and then you get less than or equal, and you get this set of inequalities from the previous one,
yes,
which is less than or equal to r over r times there is actually a subscript. The measure I sub n where I sub n is an minus bn, right?
bn minus an.
Yeah, bn minus an.
Yes, yes.
And then you can do the sum
over n.
The sum over n, and you get the measure of E is strictly less, well, is less than or equal to the measure lowercase r over uppercase r, the summation of the measures of I sub n, which is lowercase r over uppercase r, the measure of O sub n, of O, not O sub n, which is strictly less than the measure of E.
Contradiction.
By the way we constructed O.
Mhm.
And this strict inequality
Mhm.
gives a contradiction, and therefore theorem 3.4 follows. If capital F is continuous. But well, we said it's
F doesn't have to be.
because once we have it for increasing functions, we can once we know it for increasing functions, we know it for bounded variations. So what is the set of discontinuities of an increasing function, or a function of bounded variation for that matter?
What was the question again? Could you say that one more time?
What's the set of discontinuities for an increasing function or a function of bounded variation?
Measure 0?
Well, if f is increasing or of bounded variation, it has at most
Finite number of discontinuities?
not finite,
Countably many. Countably many
countably many discontinuities.
discontinuities.
Exactly.
Yes, yes. You told us last time.
Yeah, well, that's math 450A.
Yes, yes.
It's like it's one of the best things in math 450A. After the
Mean value theorem.
exactly.
Bingo! I should go buy a lotto ticket. Anyway, yeah.
Well, no, you shouldn't. I mean,
Okay.
it's obviously the mean value theorem is the most important thing of 450A, but that's so. And countably many discontinuities means that's a set of measure 0, right?
Yes.
So it's continuous except for a set of measure 0, and where it's continuous, theorem 3.4 holds. That means the statement of 3.4 is true.
Almost
So if
everywhere.
f is of bounded variation on interval AB, then f is differentiable almost everywhere, except that it's discontinuities and the set of measure 0 where the Dini numbers are not equal.
There's a less than or equal to sign, right? Instead of the equal sign, where you have the sum of the measure of IN.
Where is it?
Right above where you wrote 3 and 3.4.
There's a less than or equal sign there, I think. Yeah. M of E is less than or equal. I skipped in the book, there's 2 intermediate steps there in the inequality, but it ends up this less than or equal. So that is a less than or equal. But the important one is this strictly less here.
No, I meant the one in the middle. Isn't that
This-
one less than?
This one?
Yeah.
Yes, that should be a less than or equal to.
No, they have it equality in the book.
But why? Why is it equal?
No, because O is the disjoint union of the measures of IN.
So they're the same.
They're the same. Okay, let's erase all this nonsense.
This is for R1.
It's only for R1.
Yes.
Remember, in RD, for D greater than 1, even the statement of the theorem doesn't make sense.
Mm. Right. Bounded variation on this closed interval AB.
Yeah, nothing.
Well, so can we have something like a bounded variation on a compact set on a RD, compact subset of RD?
No,
Ah, okay.
because it depends on partitions, right? Right, well, I guess you could cook up something which is similar, but it's I don't think
not of interesting.
Yeah.
It doesn't make any sense.
Okay, so next was corollary 3.7. So the statement of this is just saying that the integral from a to b prime x is less than or equal to f of b minus f of a.
Professor, all the time less than or equal? Or...
No, it could be equal to. It's
Oh,
all
okay.
the time less. It can't be larger than or equal.
Hmm.
So that's if f is increasing and continuous. Continuous is one of those words which is really hard to spell.
OUS.
But it's UOUS.
No.
And so I want to look at exercise number which one? Number 12 for that for this. Because even if the derivative of capital F exists, it doesn't mean necessarily that f prime is integrable. And so here we look at the function capital F of x is equal to x squared times sine of 1 over x squared. This is really a calculus exercise here. When x is not equal to 0, and 0 if x is equal to 0. So if x is not equal to 0, then f prime of x we can just compute, right? That's 2x sine of 1 over x squared plus, well, actually not plus, minus x squared 2x squared over x cubed times the cosine of 1 over x squared. Right? That's the derivative. I use the chain rule here, which is 2x sine of 1 over x squared minus 2 over x cosine of 1 over x squared. And f prime at 0, we can just compute as follows. It's basically f of 0, which is 0, and f of 0 plus h, which is h squared sine of 1 over h squared over h. So 0 minus, the other way around, minus 0, which is h times sine of 1 over h squared. And if you look at the absolute value of this, this is less than or equal to the absolute value of h. And by the squeeze theorem, this goes to 0 as h goes to 0, right? So f prime of 0 is 0.
Okay.
Now, f prime of x is not integrable because of this part. And this is not integrable because the integral from 0 to 1 over x dx is infinite. And if you look at this, well, this part is okay, which goes to 0. Well, it's not really okay, but but this part, you have a serious issue as x goes to 0. So there you have a situation where you have a function which is differentiable, but the derivative is not continuous because of this part, because of the 1 over x here. It's not continuous, and the derivative is not integrable, whereas the function is differentiable everywhere.
Is this because f is not increasing, or?
Well, it's not increasing for sure, but is it even of bounded variation? So let's look at this guy again. So let me look at the partition where x over n is equal to xn is equal to 1 over the square root of pi n. Then f of xn plus 1 minus f of x is equal to 1 over the square root of pi times n plus 1 squared times the sine of 1 over, let me write that back down, times pi times n plus 1 minus 1 over pi n times the sine of pi n. And if you look at the absolute value of this is 1 over pi times 1 over n plus 1 minus 1 over n, absolute value, and 2, right? The difference between the signs is always 2. And so this is the sum n equals 1 or 0 to infinity
Telescoping.
It is telescoping. And so we get just n equals 1. I can't start at 0. And this is just 2 over pi, which is certainly less than infinity. So f is actually of bounded variation, but it's not increasing. So the reason I conclude that it's of bounded variation is because if you take the tops of the peaks minus the bottom of the peaks, that's the biggest variation you can get, right? Everything else is smaller. I take basically differences between maxima and minima next to each other. Everything else, the sum would be smaller. So it's of bounded variation, but not increasing. And that's why the increasing is actually critical for that theorem. Okay, I did assign some other problems, did I? Or not?
Yeah, you assigned 11.
12 and
13.
And 13.
11, 12, and 13.
Yeah. So let's look at 11. So there we look at the function f of x equals x to the a sine of x to the negative b if x is not equal to 0, and 0 if x is equal to 0. So first, the differentiability. Oh, actually, we want the bounded variation on 0, 1. So again, if you have sine of x to the negative b, it goes back and forth. rather quickly. The question is, so what is the biggest variation is if you take the difference between two peaks. The peaks of the sine are at n pi over 2, right?
Mhm.
So the sine of n pi over 2 minus the sine of n plus 1 pi over 2, n plus 2 pi over 2, n should be odd,
Okay.
right? In absolute value, that is equal to 2, right?
Mhm. Yes.
So we want to look at x to the negative p is equal to n pi over 2, where n is an odd number, and that means x is equal to 1 over n pi over 2 to the negative, to the 1 over b, right?
Mhm.
So if we look at the sum n equals 1 to infinity, n odd, of
Professor, I can't hear you.
haven't said anything. Sine, can you hear me now?
Yes.
Of 1 over n pi over 2. Sorry. Of n pi, and you get essentially just the sum of 2 times n equals 1 to infinity, and odd, just the odd numbers, and you get 2 over n pi to the a minus b, right? And I think there's a mistake in the problem. For that to be converging, this one, right? Because that's what I think I remember. It's not that a greater b, it's that a has to be greater than b plus 1.
Okay.
This converges, and it's the worst case scenario if and only if a is greater than b plus 1. And Okay, so that's the first mistake in there. Okay, so then it is of bounded variation. So now we look at the case when A is equal to B. When A is equal to B, we have we let and alpha is less than 1. We take x to the A sine of 1 over x to the A minus y to the A sine of 1 over y to the A when A is equal to B, this thing is differentiable, right? We can take the derivative just like we did in problem number 12. We get A times x to the A minus 1 sine of 1 over x to the A plus, actually minus A times x to the A over x to the A plus 1 cosine of x to the A, 1 over x to the A. And if you look at this, this is an absolute value bounded by A plus A over x, right? But as x goes to 0, the A over x is no good. Actually, let's forget the derivative. This is not a good thing. So if you look at this, and let's look at it in absolute values here. So the biggest this can be is 2 times x minus y to the power A. Everyone sees that?
Yeah.
Yes.
When the sign is first sign is 1 and the second sign is -1.
Right. And then x to the A minus y to the A is less than x minus y to the power A.
Mm-hmm.
And so this is Lipschitz continuous. Lipschitz is spelled differently.
We get it.
With exponent A but not of bounded variation. I mean, in problem number 12, we looked at A equals B equals 2, right? In this case. And we found it's actually differentiable, right? Everywhere. But it's not of bounded variation because the derivative is not integrable.
Oh,
And did I say 13?
yes.
Did you read about the Cantor-Lebesgue function?
It was part of this reading assignment.
It was part of the reading assignment, but we didn't have absolutely continuous in there, right? In the reading assignment.
Absolute
So-
continuity came out early on, and then you gave us Radon-Nikodym theorem.
Right. Right. I mean, well, absolutely continuous is if you have a bunch of disjoint intervals, AK, BK.
Actually, Professor, absolute continuous was not part of the reading assignment.
I know.
Oh.
I know. So I'm doing that. If for every epsilon greater than 0, there exists a delta such that if the sum of those intervals is less than delta, then the sum of the f of bk minus f of ak is less than epsilon.
Oh.
Okay. And for the Cantor-Lebesgue function, to show that it's not absolute continuous, is you use the AK and BK, you use the intervals, the endpoints of the removed intervals in the Cantor set. And between those endpoints, f of bk minus f of ak is rather large, whereas bk minus ak can get rather small, right? And that means you can find an epsilon naught such that for any delta, this sum is greater than epsilon naught. But it was not of the reading assignment, so you're not going to care about it. Right. Okay, so let's see, what are we going to do next?
Actually, we care about it, Professor. So, so function f is not absolutely continuous. Then you can find epsilon naught where the second inequality, the second one is bigger than epsilon.
Well, not absolute continuous would say there exists an epsilon naught greater than 0 such that for any delta, the second inequality, my stylus is giving out. I hate it when that happens. Happened to me in Math 102 the other day. This is greater than or equal to epsilon naught.
Even if bk minus ak is less than delta.
Even if bk minus ak is less than delta.
Oh, okay.
Well, the thing is, you can find with the Cantor-Lebesgue function, you can find the sum of f of bk minus ak adding up to 1 all the time, no matter how small delta is, right? If you look at the endpoint of the removed intervals. I mean, actually, the starting point of a removed interval would be the pk, the end point of the previous removed interval, whereas the lengths of them, since the non-removed intervals, the lengths of them have measure 0, so they add up to 0. They get smaller than any delta.
Mm-hmm.
So let me just see. If you just look at the starting set of the Cantor set, if this is B and this is A, now in the beginning this is difference is 1/3. The Cantor-Lebesgue function here, or the toy function which constructed it, would be this, right? And you look at, this is BK, this is AK. You always end up to 1 here, right? Wait, no, that's not the Cantor-Lebesgue function. Cantor-Lebesgue function is this. If you start out in the starting point, would be this. You go up to 1/2, you're constant in the middle third, and then you go up to 1. And if this is B1, A1, A2, B2, then you see that the sum here of this sum, well, you don't need a summation sign here. B2 minus A2 plus B1 minus A1, this sum is equal to 1/3, but f of B1 minus A1 plus f of B2 minus A2 what did I just do?
Is always 1?
No, it's always 1. And then if you go further in the construction, my stylus is going out. So if you go further in the construction, the sum of the f's, of the differences of the f's will always be 1, but the differences of bk minus ak, the sum, will basically go
0.
down to the measure of the Cantor set, which is 0.
Okay.
And then that, yeah, my stylus is gone. I hate that when it happens.
Oh, okay. So that's why this Cantor-Lebesgue function is not absolutely continuous.
It's not absolutely continuous.
Professor, I have a quick question. So you mentioned that when the derivative is not integrable, then the function is not bounded variation. Is there something similar to like a check where whether the function is a bounded variation or not? Other kind of tests that we can conduct?
Well, I mean, it's a bounded variation if the derivative is bounded.
Oh, okay.
And that's an easy check. You know,
if it is not bounded, then it's not of bounded variation.
Right.
Okay. Even though it's bounded, if it is not integrable, it's not of bounded variation either.
Yeah.
Okay. All right.
Okay. Okay, so the next reading is we're going into high numbers here. Chapter 6. abstract measure and integration theory. We're gonna have essentially 1 or 2 more lectures, and I just want to give you a taste of what abstract measure theory looks like. And so read pages 262 to where it says examples, which is on 276.
Woo, okay.
There's a lot of reading, but then there's no assignment beyond that.
Mm-hmm. Nothing else to do other than staying at home.
Just
so
reading and understand it, because there's a lot more to measure theory than what we just covered so far.
oh, okay.
And I will see you Monday. Angela, have you recorded all this nonsense?
Yes, sir. I have recorded. Should I stop recording?
You can stop recording now.